Good morning and good afternoon, RSGA STEM class, and whoever decided to watch this video. And welcome to our next video on motor vehicle motions. In this video, we've already experienced what it means to convert chemicals into, well, power, if you will, and we looked at what makes power in an engine, right? Looking through the lens of physics, science, motion, so on and so forth. So, with regards to the engine, in this video, we're going to explore horsepower and torque. What do those two terms mean, and why are they important regarding cars? Now, here's the important thing, right? The engine creates the horsepower and the torque, right? It's the entire process. The horsepower and torque are the result of the process, right? Of the process of turning fuel and motion into a rotational force. Now, the cool thing is that if you have rotational force, you can measure that not only at the engine, but at the wheels or where the tires meet the road. All right, really, really cool phenomenon. And we're going to go ahead and explore that in more details. All right, so real quick, the science of horsepower and torque. All right, so anytime that you buy a car, or anytime you look at a car, or you watch a review on a car, you're going to hear about the horsepower and the torque, right? Now, here's the thing. Those high-powered National Hot Rod Association drag racing cars, they have a lot of horsepower and a lot of torque, but they do different things. Now, in the world of, say, Formula One, all right, those have a lot of horsepower, but not as much torque. In the world of motorcycles, because the vehicle is lighter weight, it doesn't take as much power to get rolling, right? So we're going to explore those in more detail. And the biggest thing is to know that there is horsepower that's applicable to be used on the roads and the roadways safely, and there's horsepower that's really meant to be unleashed at a racetrack. That is really, really important. All right, so here we go. Horsepower itself is a unit of measure for power. It represents the rate at which work is done. So here's we go. All right, so in this image, I chose this image on purpose. Here we have literally a horse, right? It is pulling, okay, through a pulley, if you will, here, just kind of hanging out there in the open. If this was really real life, it would be attached to a structure, and then it is moving a set weight. All right. So here's the deal: 1 horsepower equals the ability to move 33,000 pounds 1 foot in 1 minute. Okay. That means if you are using, say, your gasoline hand mower or your gasoline push mower, and it has, say, 5 horsepower on it, when that engine is at full throttle, okay, not just an operation speed, but at full throttle, then that means you can take this, all right, this weight here, 33,000 pounds, okay, and move it 5 feet. Or you could think of it as the ability to move it 1/3 in about a fifth of the time. Okay. So there you go, in the course of a minute. All right. So again, the ability to move it 1 foot with no other friction other than gravity, because it's the weight, right? The weight, not the mass, the weight. 1 foot in 1 minute. A horse can do that in about a minute. All righty. Now, you can see this calculation over here as well. This is a whole lot more complex, okay? But basically, we have, I'll use this one here, right? Horsepower equals force in pounds over the time, all right? Distance, time, so on and so forth. Force in pounds times the distance over time, all righty? And then, of course, if you were to calculate this using algebra, you could use this down here. What do I need you to know for the 6th grade? Well, basically, it's the ability to move this weight with the horse, all right? And it might be important to know this as well for future reference. Alrighty, so let's go ahead and look at the next slide. Now, torque is the twisting force. All right, so it's the force that remember we're talking about rotation, that crankshaft rotation occurs, right? In other words, the pistons fire down. We learned in the last lesson, those fire to the crankshaft turns, which eventually spins the wheels, all right? Torque is the twisting force, all right? For cars, it represents how much twisting force is applied at the crankshaft or at the wheels in any given moment. It is measured in foot-pounds, a pound of force applied by a foot of leverage. In other words, if you had a big old wrench on a nut there, okay, and it was 1 foot in length, okay, it would be the force to move it, 1 pound, all right? Torque is the moment of force, which is a rotational force. Torque can be measured or calculated with force times the length. All right, now, if you are in class and we've already presented the levers, you know that a longer lever can create more force on an object, right? But for its most simple force, it's the amount of force that's applied here at 1 foot in length with 1 pound of force applied, okay? So there we go, okay? Now, some think of it like this, okay? Torque is the ability to get the car moving or accelerate, right? And then force or horsepower is the ability to keep it moving and going. And I know that's kind of complicated in its idea, but that's how some people like to think about it. All righty. So there you go. Now I'm going to go ahead and turn it over to a really quirky video that might sum it up a little bit better than I can. Now, when you watch this video, I highly encourage you guys to think like a little bit more adults because there is some humor in here. You need to think with the adult hat. So let's go ahead and check out that video.
Drag racing, NASCAR, rallies, racing! Awesome cars make awesome power. And you know how we compare them with stats. But what's it really mean? We're about to find out. We're talking about horsepower and torque. The way Tony talks about it, torque is a grunt. And horsepower is screaming! Torque and horsepower are both ways of measuring force. Torque measures twisting force, and horsepower measures work. And work is force over time. So let's start with torque. You probably heard of foot-pound. Pound is a measure of force. If you weigh 180 pounds, that's because your mass, what you're made of, is exerting 180 pounds of force on the earth. A foot-pound is a pound of force amplified by a foot of leverage. This is Jesse's toolbox, and this is a weird bolt in a board. This is a wrench. If I use a foot-long wrench and apply 1 pound of force at that bolt, I'm applying 1 foot-pound of torque on the bolt. If I use this 2-foot bolt buster and apply 1 pound of force at this end, I'm applying 2 foot-pounds of torque. If I apply 2 pounds of force at 1 foot, its force on the bolt is the same as 1 pound of force from 2 feet. 2 foot-pounds or pound-feet. It's the same unit because it's math. The distance from the point of measurement amplifies the force through the lever arm. I wonder where it all goes. Engine torque measures the amount of this force that an engine can produce. Let's get inside there. The pistons drive this crankshaft. You can see that where it attaches turns around this center axis, just like the wrenches turned around the bolt. Each explosion in the cylinder pushes the piston down with force. That force is exerted on the crank pin and transferred to the shaft to get it spinning. Torque is determined by 2 factors: the amount of force on the crank pin, which comes from the piston, and the distance of that force from the center axis, or throw, which varies by crankshaft. Make sense? If the throw stays the same and we produce more force from the piston, maybe with more displacement, we can increase the torque. If the force from the piston stays the same, we can increase the distance of the pin from the crankshaft center to increase torque. There's millions of combinations and variations that we can tweak to adjust the force exerted on the crankshaft, from the number of cylinders to the shape of the engine, even to the type of fuel we use, which we can get back to in a minute. Horsepower is a measurement of work, and work is force over time. James Watt lived from 1739 to 1819, and he loved doing math. Steam engines were changing everything during the Industrial Revolution, and Watt wanted to give people a way to measure all of the work that was getting done. Watt was watching work ponies, which are not tiny horses. Ponies are their own thing. You can look it up. But he noticed that a pony took about a minute to raise 220 pounds of coal out of a 100-foot well. And being a scientist, he increased that number by 50% because a horse is about 50% bigger than a pony. Whatever, it's a unit. As long as it's consistent, it can be whatever he wanted. He figured that one horse can do 33,000 foot-pounds of work every minute. A horse exerting 1 horsepower can raise 330 pounds of coal 100 feet in a minute, or 33 pounds 1,000 feet in a minute, or 1,000 pounds of coal 33 feet in a minute. That's work. That's horsepower. The amount of force, foot-pounds, torque produced over time is horsepower. Because torque is how much force an engine produces, horsepower is how quickly it can produce how much force. We can dive into this by looking at how we measure car horsepower on a dynamometer. You can either put the car on a roller that'll measure the force produced at the wheels, or if you attach a shaft to an engine, you can measure the force driving the shaft and its speed. Start your car, you put it in neutral and floor it, well, the engine would run so fast it'd explode. A dynamometer applies a load to the floored engine and measures the speed it moves. You can hook an engine to the dyno, floor it, and use the dynamometer to apply enough of a load to the engine to keep it at, say, 7,000 RPM. You record how much load the engine can handle, and then you apply additional load to knock the engine speed down to 6,500 RPM and record the load there. Then even more to get it to 6,000, and so on. You can do the same thing starting at 500 RPM and then work your way up. What the dynamometer is actually measuring is torque. And because of math, to convert torque to horsepower, you just multiply the torque by the RPM and divide it by 5,252. That's horsepower. Why 5,252? Well, I'm glad you asked. You remember the horse from before with the coal? Okay. That horse moved 330 pounds 100 feet in a minute. So 33,000 foot-pounds of work in 1 minute is 1 horsepower. Now, for my dumb brain, let's use 100 pounds 330 feet in 1 minute, because that's also 1 horsepower. We need to show 330 feet in 1 minute as revs. So let's think of the wheel. The distance traveled in 1 revolution would be 2 pi r, or 6.28316. 330 feet in revolutions is 52.52. Starting to look familiar? 100 foot-pounds at 52.52 RPM is 1 horsepower. Therefore, 1 foot-pound at 5,252 RPM is also 1 horsepower. So you take the torque, multiply it by the revs, and divide by 5,252, and you've found horsepower! Woo! Woo! Oh, yeah. When you plot horsepower versus the revs per minute for the engine, you get a curve like this one. An engine has peak torque, where it generates the most force. It has peak horsepower, where it produces the most torque most quickly. When you're trying to accelerate quickly, you want to try to keep the engine close to its maximum horsepower point on the curve. That's why you downshift to accelerate. By downshifting, you get closer to the peak horsepower on the curve. You want to launch your car from a stop? You rev the engine to get it right at peak torque. Then you release the clutch to dump maximum power to the tires.